Okay, so here is the quiz, the CFU from class today. This is randomized. This is just the versions that it gave me, but yours should look similar. So let's go ahead and work through this. The first question looks like this, and it says, a student conducts an experiment to see how changing the mass of an object in uniform circular motion affects different aspects of its motion. The student performs two tests. Object A uses mass m and object B uses mass 3m as shown above. So again, you can see that in the picture that we have object A has mass m, object B has mass 3m, and otherwise everything else appears to be the same. And then it tells us to complete each statement below by selecting the correct relationship for the above scenario. So when we're looking at objects in uniform circular motion, we have some formulas that we can use to analyze this. The first question is specifically asking us to analyze the effect on force, and it's talking about changing the amount of mass and how that is going to affect the force. So again, we have this equation, one that you should be pretty familiar with, F equals ma. And when we look at that equation, we can see that if we were to alter the amount of force here, or mass here, that it should alter the amount of force as well. Let's see. Oh, as object B, they're comparing the two. All right, and so if object A has m and object B has 3m, then it's asking us to compare object A to object B. So object A has 1/3 the amount of mass as object B has. Because of that, the force that it experiences will also be 1/3 as much because the mass and the force are directly proportional to one another. In class, when we looked at a lot of these relationships, we looked at the equation written like this, F equals m, and then we had v squared over r, because again, this is acceleration. So depending on what variable you're looking at, this might be a good thing to analyze as well. So if you're trying to figure out the effective radius or something. The second question, though, is about how changing the mass affects the acceleration. And if all else is equal, this is the acceleration equation. Again, I just plugged it in here, but acceleration is v squared over r. And you'll notice that the factors that affect acceleration don't include mass. The factors that affect the amount of acceleration that an object experiences are the velocity that it's being swung at and the radius that it has. And so changing the mass should have no effect whatsoever on the acceleration, meaning that they should have the same acceleration as one another. It's not even in the formula. All right, so that's the answers to number 1. Number 2 looks like this. Again, it is randomized. Yours might have different numbers, but it says two objects, one having a mass m sub a and the other m sub b, are distanced d away from each other as seen below in the first diagram. So that's the top picture that we see here. Then it says if they are moved so they're now half as far away, so they're closer together, half the distance, how much did the force of gravity change between them? So this is asking us to look at how the distance of separation affects force of gravity. And that's not these formulas. That is the universal law of gravitation. So we're going to go back to that formula. The universal law of gravitation was this one. And it's written different ways and different charts. Sometimes I have an R down here, but it's the same thing. It's the distance of separation. I use D because they're using D here. Sometimes the G is written in front of the fraction, but this is mathematically the exact same thing. And we can analyze it using the equation like this. And so the question is, if we have half the distance down here, what does that do to the force? And I can tell that the relationship between force of gravity and distance is an inverse square relationship. I can tell it's inverse because as I increase this, this will decrease. I'm dividing by a bigger number. So inverse, they're going to be opposite. When one goes up, the other goes down and vice versa. But it's not happening linearly because this is squared. So it is both inverse and squared. Again, if they give you a factor and you're looking at an inverse square relationship, flip your fraction and square it, or square it and then flip it. It's the same thing. So if I flip that, that becomes 2 over 1, which of course is just 2, and then square it, and I get 4. Okay, and so that's how you're going to handle those inverse square relationships. So this increased the force by a factor of 4 times its original amount. And that's what you should have for number 2. All right, number 3. Number 3 is yet another example of an object in uniform circular motion. It says a 0.13 kilogram ball tied to a string moves in a circle that has a radius of 0.4 meters. And then it tells us the ball takes 2.79 seconds to complete each rotation. What is the object's average speed or tangential velocity? So we're going to be trying to find tangential velocity. And again, we have a couple of equations in our uniform circular motion unit that have velocity in them. We know that tangential velocity is equal to 2 pi r over period. So if we happen to know the radius and the period, this is a good equation to use. We also have tangential velocity showing up in our centripetal acceleration equation, v squared over r. And we could, if we know the acceleration and the radius, solve for v. Based on this particular question, it does look like they gave us both the radius and the period, meaning they gave us that and that. And so we're going to use the first equation that I have here. And we're going to say that the velocity is equal to 2 pi times the radius, which it says is 0.4 meters. You do want to double check your units. Meters is what we want. Divided by the period, which we do want to be in seconds, it is 2.79 seconds. Okay, so that would be your substitution step, and then you just go to your calculator. 2 times pi times 0.4 divided by 2.79. Okay, and it should give you, and it does, that value. 0.900815. It keeps going, but that's what this says, 0.900815. And again, velocity should be in units of meters per second, which we have because this one is in meters, this is in seconds. Those are your units. All right. Question 4. A car travels around a curve at constant speed of 100 kilometers per hour. Which of the following must be true? So this is just a concept question about objects in circular motion. Okay, if you have an object in circular motion, it is accelerating. That, yes, the speed is constant, but you're turning. So this statement, the car is accelerating, has to be a true statement. I'm going to check it for now. F net equals 0. That can't be true. It is impossible to have acceleration without also having a net force. So that second statement is wrong. The forces are balanced. Again, that would mean the net force is 0. That says the same thing as the statement above it, which is not true, because if you have acceleration, you have to have a net force, which means you have to have unbalanced forces. And obviously it can't be all of these above. So it just is this one statement, the car is accelerating. Question 5. Suppose that two objects exert a gravitational force of 18 newtons on one another. What would that force be if the mass of one of the objects changes by a factor of 1/3? Okay, so this is a proportional reasoning question, again going back to the universal law of gravitation. That equation looks like this. And if you want to write r down there instead, by all means, please do so. Distance of separation happens to be the radius of an orbital path if you're dealing with that, or the radius of a planet if you're on the surface. So sometimes there's an r here. There was in our notes. All right, this one is asking if the mass of one object, so it doesn't matter which one, pick one. Let's say that is 1/3 as much. what is going to happen to that gravitational force? Okay, in fact, not what happens to it, what is the new force? What would that force be? Well, you do need to see, and you can tell by looking at the equation, that force and mass are directly proportional to each other. So if you have 1/3 the mass of one of your objects, it will give you 1/3 the amount of force of gravity. Again, it's directly proportional. So because the original amount of gravity was 18 newtons, we just need to divide that by 3 or multiply it by 1/3, same thing. Okay, but that would give us 6 newtons. Alternatively, you could put in some fake numbers, solve, and then solve again. I don't know why you would do that. This is going to be the way you want to go. 6 newtons is your answer. Number 6. Number 6 says, a moon has a mass of 8.55 times 10 to the 18th kilograms, while the nearby planet it orbits has a mass of 9 times 10 to the 25th kilograms. These two masses have a distance between their centers of 2.76 times 10 to the 7th meters. What is the magnitude and direction of the force that the planet exerts on its moon? Okay. So this is very similar to some of the other problems that we have done in class. They gave us masses, they gave us a distance of separation. The force, again, we're looking at the universal law of gravitation, which I had just written out. Let's go ahead and solve for it again. So the force of gravity would be equal to our constant, 6.67 times 10 to the negative 11th, multiplied by the product of our masses. We have two masses here. It does not matter which order you write them. I'm going to do them in the order they're written in the question. 8.55 times 10 to the 18th. You do need to check your units. We're already in kilograms, so we're good. And then the other mass is 9 times 10 to the 25th, also already in kilograms, so we're good. And then we're going to divide all of this by the distance squared. The distance does need to be in meters, and a lot of times that requires a conversion, but not this time. I gave it to you in meters. So 2.76 times 10 to the 7th squared. All right, so that's what goes into the calculator, and that is universal law of gravitation. It will allow us to solve for the force of gravity. All right, so I'm just going to type in all those values. This is what I got from my numerator, and now I need to divide by that denominator and make sure you only square the denominator. 2.76 times 10 to the 7th. Sorry, I keep typing the wrong thing. There. Squared. And I am getting that. Let's see if it's the same. It is. Again, when you're typing this in here, you can use the E just like my calculator does. It does tell you, and it says that here, scientific notation can be entered using a capital E, round the coefficient to exactly 2 decimal places. So exactly 2 decimal places in this case would be 6.74. If you type 6.73, it will count it wrong. Then the E and then the 19. You don't have to type the plus sign in front of the 19. That's the magnitude. It tells us magnitude and direction of the force the planet exerts on the moon. And so the planet would exert this force on the moon, pulling the moon toward the planet. Your options are pushing it away or pulling it towards. So obviously it's pulling. Or cannot be determined, which is not true. All right, so that would be what you would want for the first part. The second one says, what is the magnitude of the force that the moon exerts on the planet? So this is the force the planet exerts on the moon. So if I were to compare the force that the moon exerts on the planet, again, I would say that they are equal to each other. This is a force pair. Don't fall for it. I know they have different masses. The moon is a lot smaller, but the forces are equal and opposite. Newton's third law. What type of force allows the moon to orbit the planet in this circular path? It's basically asking what is the centripetal force, and for every single object in orbital motion, if it's in orbit, it's gravity. So that should be what you select there. Oops. Oh, I forgot to type in the unit. or the direction, sorry. Pulling the moon toward the planet. All right, there we go. Okay. Question 7. A ball on a string is being swung around in a circle as shown below from a bird's eye view at a constant speed. If the string is released at the current position, which way would it travel? Anytime we're looking at this, you need to think back to Newton's first law. An object in motion will continue in motion with a constant velocity, that means constant speed straight line, unless an external force acts on it. There's a string here acting on it, providing an external force of tension, pulling it inward, and that's why the path bends, because this ball wants to fly off in a straight line, and yet it keeps being pulled inward. That's your centripetal force, and that is the main idea behind all objects in circular motion, is there's this force causing their path to bend. Okay, but if that force isn't there anymore, then yeah, you're going to have an object in motion remains in motion in a straight line at a constant speed. So the straight line at this point is the tangential velocity. So whenever we look at an object in circular motion, and this one is moving in a clockwise direction. I just drew that backwards, sorry. Okay, look at the direction of the arrowheads. That's going to affect your answer. Okay, so this is the direction that it's going at those different points, and it's asking about, hey, what happens here? Okay, again, it will be tangent. Your tangent line, if you find the center of your circle and you draw in a line of radius to your object at the point you're being asked about, your tangent line is always 90 degrees. So the tangent line looks like that. It would go like this. Okay, however, you need to figure out, is it going to go this way or this way? Well, based on the direction that this thing is rotating, whenever it gets to this point, if the rotation is like this, in this clockwise direction, well then this would be the direction it would fly off at that point. Okay, so don't draw it backwards. It's not going to go that way. It's going to go off in the direction it's already moving at that point in time, which based on the clockwise rotation would be at a diagonal up and to the right, which is this picture here. But that right there that we just drew in, this is the tangential velocity. All right, number 8. A bucket is whirled around at the end of a string in a circular path. What is the direction of the tension force acting on the bucket? That tension force, whenever you're whirling something in a string, and the force of tension is the centripetal force. The force is always inward toward the center of the circle. So if this is my bucket on the string, this might be the direction it would fly if it was released, but that's not what this question's asking. This question is asking, what is the direction of the force? And the force is what keeps it in that circular motion to begin with, and it's always inward toward the center of the circle. Okay, so your force vector is always drawn inward toward the center of the circle. It's called a centripetal force for a reason. Center, centripetal. It's always inward toward the center of the circle. Direction of the tension force, inward toward your hand, because your hand is at the center of the circle in this diagram. All right, question 9. This is similar to question 1, except question 1 we altered the mass, and in question 9 we are altering the radius. I think I need a fresh sheet of paper though. So let's get us a new sheet of paper in case we need to work anything out. All right. This one says, a student conducts an experiment to see how changing the radius of the string holding an object in uniform circular motion affects different aspects of its motion. The student performs 2 tests. Object A uses radius r, object B uses radius 3r as shown above. Again, you can see that in the picture. By what factor does the acceleration change? So here we're just looking at what is the relationship between acceleration and radius. And if we look at our equations, the one that we want to look at specifically that has those 2 variables in it is this one. Okay, so what is the relationship between that acceleration and that radius? Well, acceleration and radius are inversely proportional to one another. Increasing the radius means dividing by a bigger number, which means a smaller acceleration. So they're opposite each other. Therefore, if I was to have 3 times the radius, I'd be dividing by 3 times as much, And if I divide by 3 times as much, I expect to get 1/3 the amount of acceleration. So by what factor does the acceleration change? It should be 1/3 as much, which is in fact the answer to this question. All right, last one, number 10. A distant planet with a mass of 6.43 times 10 to the 23rd kilograms has one moon that orbits at a distance of 9,959 kilometers. The mass of this moon is 4.02 times 10 to the 17th kilograms. Find the gravitational force acting on the moon, the acceleration of the moon, and the tangential velocity of the moon. We have seen questions like this a couple times, and I told you guys that you would see a question like this as your FRQ as well. This was the warm-up question, and it's also going to be, and you also saw it in the notes. Okay, so if we take a look and we're looking for gravitational force here, we're going to start by finding force of gravity. So this is actually kind of walking us through it in a nicer way because it's telling us, hey, we need gravitational force, which means we know that we're going to go back to the universal law of gravitation. And again, you can put a D down there if you prefer. I've written it both ways while I've been filling this out, but that's the universal law of gravitation. So if I were to substitute in, and I'm looking for gravitational force, G right here, remember, is a constant. It is 6.67 times 10 to the negative 11th, and then I have my masses. My masses do need to both be in kilograms, which they are. 6.43 times 10 to the 23rd, and 4.02 times 10 to the 17th. And then all of that over the distance between them squared. Now the only problem with that is that they gave me this distance in kilometers. And I don't want it in kilometers, it needs to be in meters. So we need to multiply it by 1,000, which means I just need to add 3 zeros, 9959000. And that'll be in meters, and again it's squared. Don't forget to square this. A lot of people miss it just from simple thing like forgetting to press that one button. All right, so let's go ahead and solve. 6.67 times 10 to the negative 11th times 6.43 times 10 to the 23rd times 4.02 times 10 to the 17th. That's my numerator. Divide all that by my denominator, which is going to be 9,959,000 squared. And again, double checking, make sure I typed it right, and we get this. Force of gravity, I'm getting that. Let's double check. Yep, that looks right. I have the same exponent, and 1.738 looks exactly the same. All right, next question says, find the acceleration, okay, of the moon. So here's where you have to be able to see the connection. And this is where a picture comes in handy. I'm going to draw it up here. If you draw a picture, let's start with a circle. All right, and this is talking about a planet and a moon. So here's my planet. Okay, and then my moon is somewhere in orbit around it. It doesn't really matter where we draw it. Let's draw it right there. Moon. Okay, the distance that they gave us for the distance between them, right here, is the radius of the circle. And this is why it helps to draw a picture, because if you don't draw that, you might not see it. But again, that's why I like using R down here. It is a radius. It's the radius of the orbital path. So this distance right here is this distance right here. It also is the radius of the orbital path, and that means it's something that we can use in our circular motion calculations, which is what we need to find acceleration. Okay, now acceleration, obviously it's in this equation, but I don't know velocity. I do know the radius, but I don't know the velocity, so that one's not going to be helpful. But there is an equation that is helpful, and it's one you're actually more familiar with, F equals ma. If you know your centripetal force and you know your mass, you can find your centripetal acceleration. And I do know my centripetal force. The force that pulls this moon inward is Fg. That is my centripetal force for any object in orbit. Okay, so that force, that inward force here, that is Fg. And so I know this. I can take my answer from the previous question. It's still on my screen over here. 1.74 times 10 to the 17th. And I can set it equal to mass and then solve for acceleration. But which mass? I have two masses here. Well, it wants the acceleration of the moon. So we need to use the mass of the moon. The mass of the moon of these two numbers, it's the smaller one. It's that one right there. You can see it in the question too. But the mass will be 4.02 times 10 to the 17th, and then A. So that is your substitution step. So we're going to divide our answer to the previous question by this value here. And I'm not going to use the rounded value. I'm going to use the value on my calculator screen, because if I use this one, I'm probably going to have rounding error in myOpenMath. So only round at the end when you're using myOpenMath. Again, when I divide them, I get that. Let's see what it says. There we go. 0.4324, it keeps going. Notice it also accepted a negative, because depending on where it is in the orbit, if you drew it over here and here it's pointing to the left, if you wanted to call that negative, here it's pointing to the right, it really just should be asking for the magnitude. But I accepted it either way because of that issue. All right, last question says, find the tangential velocity of the moon. So now that we know the force and the acceleration, we can look at our equations and see which one we can use to find tangential velocity. Again, there are two formulas that have tangential velocity in them. This is one of them. The other one is tangential velocity equals 2 pi r over period. I can't use that formula because I don't know the period. So I can't solve for tangential velocity with this, but I can use this because I do know A, we just found it, 0.432, this value over here. And I do know the radius. Again, that distance it gave us is the radius. So we're going to go and use A equals V squared over R. Okay, and we're going to use the acceleration that we just found, which was 0.432 equals V squared. We're looking for that, specifically for V. And then the radius, again, don't use this. You don't want to use it in kilometers. We already converted it once, right there. So that's the value we want in meters. We're not squaring it this time, but we want it in meters. Okay, and it was the 9,959,000. All right, so that is your substitution step. From here, you're going to multiply both sides by that value. So we're going to take our answer in the calculator screen. Again, don't use the 0.432. Use the whole number, the answer from above. And we're going to multiply it by that. I don't think I have it in here because I did that in my head. That's fine. By 9,959,000. And when we do that, we get V squared equals 430,646.513. Again, that's not our answer, that is V squared. So our last step is to get the square root of that, and that should be our velocity. 2075.2. 2075.2. And again, it's accepting it either way because, again, the direction is changing. It's moving in a circle. So it positive, negative, it doesn't matter. It really just wants the magnitude. All right, so again, the velocity was 2075.2 meters per second. All right, that is it for this CFU from class. It is going to look similar to the types of questions that you see on the test. In addition to looking back through these, I would recommend that you look at the videos where I went over the half-sheet warm-up quiz, those little free response type questions, as well as your past problem sets for this unit, and of course your unit summary. Unit summary is great if you end up needing a daily grade redo. Maybe the CFU didn't go so well, or maybe the little warm-up quiz didn't go so well. Then please make sure that you work on that. And if you're looking for extra practice on universal law of gravitation specifically, then don't forget that you have that weights on other planets assignment that we ended up canceling because of the school closure on Monday, but the assignment's still there. You're welcome to use it for extra practice.